Let's resume our discussion on Taylor series and Taylor polynomial. In the first video clip, we talked about Taylor series theorem and its proof. It goes like this. If you have a function that is represented by a power series within a certain radius of convergence, the coefficient an satisfies this equality. An is equal to nth derivative evaluated at the center C over n factorial. Usually, this is not a good way to calculate an if you can find out all those coefficients from alternative methods like geometric series formula and integration and things like those, like log function or arctangent function and so on and so forth. That's usually easier. But in some other situations, you may have to take the derivatives repeatedly to find out an. That usually is very tedious computations. However, in some cases, they turn out to be okay. Here are three such examples. E to the x function, cosine of x function, sine of x functions where c is equal to 0. And these three expansions are called Maclaurin series expansion, and they are important. The radius of convergence is infinity to all those. And then in the second video, we talked about binomial series expansion. 1 plus x to the k power turns out to be infinite sum of binomial kn x to the nth power. And of course, if we have x minus c, for example, here instead of just x, then this will be x minus c to the nth power, a little bit more generally. And what is binomial kn? It is defined kind of like this. When k is a positive integer and also n is a positive integer, as a matter of fact, n is non-negative integer and greater than or equal to 0 and less than or equal to k, then this binomial kn can be written as k factorial over n factorial times n k minus n factorial. However, when k is not a positive integer, then this expression does not make much sense, but this one does. Also, please note that when k is positive integer and n is an integer that exceeds k, then k minus k will be found somewhere over there. So binomial kn is 0. So the summation actually brings down to summation n from n is equal to 0 to k, consequently yielding the binomial theorem. In general, however, we have binomial series expansion, kind of like this or that. We went through several examples and some trivial examples where we just plug in negative x over 2 in place of x to get Maclaurin series expansion for this one, or just replace x by 2x for cosine, or we had some clever computation like this. We had to manipulate the inside so that it is 1 plus something so that we can apply the binomial series expansion theorem. When c is not 0, then the computation is far more complicated. And what can we do? We'll have to simply do it by repeated differentiation, which can be really pain in the rear end. But, well, if you have to, then you have to. Here are two such problems. This one, on the other hand, was far more clever problem, to tell the truth. We have a trinomial down here, but it is possible to manipulate it so that this is a complete square plus something, and a further manipulation yields we have 1 plus the complete square and total to the negative 1/2 power, so that we can apply the binomial series expansion theorem centered at x equal to negative 3 like this. And now let's move on to some integral problems regarding series expansion. How about the first problem? If this had been x times e to the negative x squared, you can do it by substitution, u equals negative x squared. But this one is going to be impossible in traditional means. So how do you handle it? We can use the series expansion of exponential function here and replace x by negative x squared. And that's how we get this series expansion, and consequently we have x to the 2nth power. Taking the antiderivative term by term, we have to increase the power by 1 and divide it. Speaking of increase, let's increase the font. And we end up with this series expansion form. And this is perfect, but if you want first several terms, here they are. Now, if you want a definite integral, what do you do? In that summation, infinite sum, apply the fundamental theorem. Plug in 1, plug in 0, subtract 1 from the other. If you plug in 0, you're going to get a bunch of zeros because even the starting number is 0 to the first power. If you plug in 1, then 1 to whatever power is always 1, so highlight part drops out, and we just end up with this numerical series. This is perfect. But if you put first several terms, here they are, and here's approximate computation. If you want some computation for this kind of situation, you can take first 100 terms or things like that with computer. Mathematica automatically does that. What if you have this kind of integral? This integral is important in physics. It is called sine integral function, I think, and it is used in optics and electromagnetism and things like those. By the way, the previous integral, this one was even more important. And this one is used in statistics and physics and yes, especially statistics. Gaussian function it is called. It is even more important. Let's come back to this one. Let's expand sine function using the Maclaurin series expansion. Here it is. Sine changes plus minus, plus minus, plus minus, alternating sign. All the powers are odd and all those odd factorials are down there. Division by x basically means you have to drop all the powers by 1. So instead of 1, 3, 5, 7 powers and so on, we have 0, 2, 4, 6 powers and so on. So after taking the antiderivative, we have something like this. And then if you put everything into the summation notation, you have something like that. You can do something similar with the last problem. In the expansion, Maclaurin expansion formula for cosine, you can replace x by x squared and then multiplying by x squared again, which means raise those powers by 2 again, and then apply antiderivative formula to each term, term by term. Now let's go over to Taylor polynomials. And this is gonna be a rough topic, and we'll have to skip a lot of things here. Here is Taylor's theorem, and this is far more general than the previous Taylor series theorem, which was valid only when the original function had power series expansion. In this case, we do not need power series. We do not even need infinitely many differentiable functions. We only need a function that is differentiable n times, and the nth derivative is continuous. For example, we do not even need n plus first derivative. If it exists, fine. If it doesn't exist, it's still okay. And the sum up to n minus first term is a polynomial because this is a finite term. And then the numerator of this coefficient is a derivative all the way up to n minus first derivative. If you look at this integral part, which we call the remainder, because if you approximate f of x with this polynomial, this turns out to be the difference between the two. This one has nth derivative over there, which means we just use this condition. Nth derivative is continuous, so this expression is valid. Now, how do we prove it? Wow, that's gonna be a challenge. Whew! If you're interested, you can go through with it, but I'm not going to spend class time doing that. And then, well, after some further manipulation, this integral can be rewritten like this. Very similar to the general term here for k equals to n, except for one thing, except instead of nth derivative evaluated at c, but the nth derivative evaluated at certain z between x and c. That's the only difference. The proof, well, another challenge. So as a matter of fact, this proof for the second part of Taylor's theorem should be attached to the first one. We end up with really, really long proof. No wonder Taylor's theorem is so highly praised. Anyway, if you look at, if you look at this second formation here, we can see that the remainder can be estimated accordingly. What do I mean by that? Well, if I approximate f of x using this polynomial, and this will be the remainder. Now, what is the absolute value of the remainder? Well, let's suppose that the nth derivative is bounded by a certain capital Mn in the entire interval. Then this absolute value of this remainder is going to be overestimated by Mn x minus c to the nth power in f value over n factorial. Consequently, we have a remainder estimation. The proof is actually pretty simple. This proof is not simple. This proof is not bad at all. This one is replaced by Mn, and that's an overestimation, so we have an inequality there. Let's see, let's do a application here. In Einstein's theory of special relativity, the mass can be written like this. Mass m for moving object is equal to m0, the stationary mass, over square root of 1 minus v squared over c squared. And the energy is mc squared, and that's for moving object. And stationary object also has energy, so that's m0 c squared. The difference between those two will be the energy the object gained by moving. That's called kinetic energy. And let's estimate kinetic energy like this. mc squared minus m0 c squared. And then mc squared, well, this m is nothing more than m0 times this factor, 1 over square root of 1 minus v squared over c squared, this one over here. And if we use Taylor approximation to approximate this thing, then we can take the first two terms and get a polynomial, and this is going to be the remainder. We have minus 1 coming from this part canceling out, so we have this cancellation. We have 1/2 m0v squared plus m0 c squared times r2, and this r2 is going to be very small. This remainder is going to be very small, so the kinetic energy can be approximated by 1/2 m0v squared. And this, by the way, is the same as the kinetic energy for Newtonian dynamics, not relativity, this classical case. Now let's use Taylor's inequality to estimate the difference. Now if moving object is moving really fast, then obviously the Newtonian mechanics fails, which means the remainder is going to be very, very large. So we cannot use this approximation. For relatively small velocity, it'll work out okay. And this is what it's talking about. V is less than 100, which means m2 is, in this case, 100 squared over c squared like this. And c is a speed of light. It's humongous. Do the computation, you're going to get something really, really small, so it's okay to do the approximation.